Regression analysis versus stochastic optimization. The mathematical expression of an empirical model that is frequently used in ground motion modeling is given below. In equation 2, the seismic magnitude m, distance r, km, and depth h, km, are considered to be the independent variables of the model. Equation 2. Random variables were introduced in equation 2, for modeling soil site conditions, E, and style of faulting, F. From this point on, the scientific effort focuses in solving equation 2, corresponding to the determination of the coefficients. The traditional method to determine the coefficients of equation 2 corresponds to regression analysis, whereas modern techniques of mathematical optimization are developed over the last decades. The contribution of optimization to geophysics has been interestingly growing the last decades due to its efficiently in modeling complex natural systems by determining the best solution from a set of alternative solutions. Goldberg, 1989. But which is the main advantage of optimization? The answer to this question would be its ability to reach the optimal solution for any system even under extreme computational environments, either when datasets are limited but also when vast datasets of high diversity require the determination of a solution describing sufficiently all the samples given. In the following section, the advantages of optimization versus regression would be analyzed, and the best solver for optimization process would be selected through a test involving a number of important deterministic and stochastic algorithms. Using the nonlimfit function, the implementation of mixed effects technique can be a first approach to modeling using regression analysis, leading to the determination of the coefficients of equation 2. The results, however, revealed that this method was not successful in determining coefficients E and F, corresponding to the random effects terms of the model, due to the poor representation in the database of different types of soils and styles of faulting, respectively. In theory, traditional regression analysis discussed in previous paragraph is expected to provide one possible solution for any given equation. Nowadays, optimization addresses the necessity for determining the best solution for datasets of complex physical systems. As described previously, the effort lies in determining the optimal solution for the mathematical model of equation 2, which leads to the implementation of constrained optimization techniques. The mathematical problem corresponds to the minimization of misfit represented by the sum of squares of the residuals, between the logarithms of observed and predicted values, equation 3. Constrained minimization problems have some basic pillars which are briefly given as: the existence of a candidate theoretical solution, to initiate optimization; the existence of an objective function, to evaluate whether minimizing the misfit is achieved; a set of linear constraints serving as bounds for the coefficients determination; and the determination of convergence criteria, Rothloff, 2006. It should be noted that for consistency in this example, the same objective function, linear constraints, and convergence criteria have been used during the implementation of the aforementioned solvers. Techniques used during optimization to exhaust the search space are classified generally in three classes: calculus-based techniques, guided random search techniques, and enumerative techniques. Filio et al., 1994. In this paper, calculus-based versus guided random search techniques will be tested through comparison of different solvers, whereas enumerative algorithms will be discarded since they cannot compete to the robustness race when compared with the aforementioned techniques, mainly due to the characteristics of their search domains, said, 2005. Calculus-based techniques are further divided in direct and indirect search methods. Filio et al., 1994. Indirect search methods as nonlinear least squares in this example is the most common approach in data fitting problems in earth sciences, corresponding to the implementation of the maximum likelihood criterion, Draper and Smith, 1987, for determining the best solution, setting the value of the objective function in equation 3, 20. Pattern search, on the other hand, is a direct search method used broadly in its generalized form in optimization of non-continuous and non-differentiable functions. Hooks and Jeeves, 1961, Dolan et al., 2003. An initial population of possible solutions serves as set of starting points. During optimization, the available search space is either increasing or decreasing, depending on a gradient, in the effort to improve the solutions suggested previously. Audet and Dennis, 2003. The latter are then evaluated, for their effectiveness to minimize the misfit between predicted and observed values. using an objective function, equation 3. Direct search methods are considered to be the simplest variation of deterministic algorithms used in optimization, criticized for their efficacy to search sufficiently large solution spaces, Goldberg, 1989. Guided random search techniques are classified in genetic algorithms and simulated annealing, Filio et al., 1994. Both algorithms use information in order to guide their search for the optimal solution of the system. The development, however, of genetic algorithms is based on natural selection principles, whereas simulated annealing relies on thermodynamic processes. Fogel et al. 1966, developed genetic algorithms, GA, alternatively known as evolutionary programming, as a technique in which candidate solutions to given tasks were represented as finite state machines, which were evolved by randomly mutating their state transition diagrams. Holland, 1975, focused on how genetic operators observed in nature, such as survival of the fittest, crossover and mutation, could be introduced into evolutionary computing. During the last decades, genetic algorithms applications has been described in the works of de Jong, 1975, Greffenstedt, 1986, Goldberg, 1989, Davis, 1991, discussed in Mitchell, 1996, Thorugli, pointing out their strength in determining solutions for complex natural systems. The robustness of genetic algorithms in geophysics has been only recently described by researchers, Stofa and Sen, 1991, Tavakoli and Pisch, 2005, making the aforementioned solvers known for their application in constrained minimization problems, Goldberg, 1985. GAs are not limited by restrictive assumptions, concerning the continuity, the existence of derivatives and the unimodality of the function in terms of computational geometry. This is an advantage over regression analysis, which often determines local minima as the solution of a given equation, Goldberg, 1989, while at the same time the suggested solution is highly dependent on a single point of initialization. In the following paragraph we focus on the initialization, the process of improvement and the destination of constrained minimization by using stochastic solvers such as GAs. By keeping the analogy to biological systems, a number of chromosomes/strings form the genetic prescription for the development and the operation of the organism. In our case, the chromosomes/strings are composed by 6 genes/characters, representing the set of coefficients of equation 2. GAs start with a possible solution or a set of possible solutions corresponding to a theoretic attenuation curve and continues with optimization in order to determine the optimal solution for the given data set. In this study, both initialization options have been tested, corresponding either to a single starting point, simple genetic algorithm, or multiple random generated starting points, genetic algorithm with initial population development, forming an initial population of candidate solutions, each one satisfying the given linear constraints for the determination of the coefficients of equation 2. In order to ensure well-dispersed and random initial population development, for the adequate representation of the search space, Latin hypercube sampling was used, Diaz Gomez and Haugen, 2006. The technique was elaborated by Iman et al. 1981, as stratified sampling without replacement, whereas in recent years risk analysis software employs Latin hypercube sampling in preference of Monte Carlo approach for population development. During optimization, every candidate solution/string satisfying the given linear constraints is evaluated, through the objective function of equation 3, for its effectiveness in minimizing the misfit, hence bringing the response value of the system near a desired value. Within a generation, group of solutions, fitness scaling serves the purpose of ranking each candidate solution to facilitate the selection of the best solutions that should surviving in the next generation. In that way, mimicking nature, the fitter solution survives and can be a parent individual to the next generation, whereas worst fit solutions are penalized. In the present study, a number of 200 generations is considered, each one with population size of 600 individuals/solutions. Stochastic operators like the crossover, mutation and survival of the fittest guarantee diversity of the population, Pan, 1995, forcing the GA to search the solution space intensively, thereby reducing the possibility that the algorithm will return a local minimum, Goldberg, 1985.